Okay. So this is our second video, and what I want to do is play a little bit with the models. I'm going to do more of this in class, and I'm going to give you an art lesson on how to draw a chair cyclohexane. Okay, so what you have to really do is play with your models. You want to play with a 3-membered ring. You want to play with my 4-membered ring, which I already lost. Okay, you want to play with a 5. Oh, there it is, 4-membered ring. You want to play with a 5. I have a big 5 here. And you want to play with a 6-membered ring. And kind of the way you want to play with them is kind of study what their flexibility is like by moving them. And study also, notice how the flexibility changes as you decrease carbons, down to a 4, okay, down to a 3, okay. Look at the eclipsing in the molecule. So I'm going to start with a 3. Okay, notice I can't even build this 3-membered ring with normal bonds. You guys can try it. It depends on your model kit. But my model kit is not flexible enough to support the 60-degree angle that would be required in a 3-membered ring with this kind of kit that we have. So I instead use double bonds. And that's not so inappropriate because some people believe that in 3-membered rings, the bonds are banana bonds, meaning because they can't really get compressed down, the orbitals can't compress down to the 60-degree angle, they're really, instead of overlapping in the nice end-on-end fashion that would give us a strong bond, they're overlapping a little more like that, even though they're probably not truly 109.5-degree angle. It's significantly compressed. So using what we would normally use as pi bonds like this, a banana bond is a little more like a pi bond than it is like a sigma bond, or it's right in between. So you see how they're kind of like bananas? All right. The other thing you're going to find with a 3-membered ring, unless you use the banana bonds, they're very stiff. All right. Usually in a 3-membered ring, all the if you look down, if you sight down any bond, you'll notice that the hydrogen bonds are completely eclipsed, as are the bonds in the ring. And again, I'm using these bonds because I can't build it any other way. If you go to a 4, you're going to notice a little bit of flexibility, and the molecule is actually thought to sit in what is a little bit of a V shape, kind of like that. So the way you make the V is you put all the carbons in the same plane, take 2 opposing hydrogens, and bend them in toward each other, and you'll get the rough shape of the molecule. Now, what's the advantage of this? The advantage is that it relieves some of the torsional strain. So, Clem, looking down that, can you see those are separated a little?
Yeah.
Okay. So when you look down any bond in your molecule, you'll see that these hydrogens have separated a little bit, and that relieves some of the torsional strain. And again, I want you to read and think about torsional strain. Any bond, look at every bond in the molecule, there's a little bit of relief of the torsional strain. So the butane is bent a little bit, and if you're going to draw its conformation, it would be something like that. And again, what does this do? It relieves some torsional strain. And you'll see the molecules deform themselves, but it still has very large angle and torsion. Okay? Cyclopentane, there's probably much nicer pictures of this in your book, of course, but cyclopentane is essentially, like if I were going to draw a Newman projection of it, remember Newman projections? We talked about them on Friday. We may have to go over that. Please come in like raring to go because we really got to get going. A cyclopentane, if I put it on its side like this, it would be, I'll put the other CH2 here. It would be like that, and they're really eclipsed. It's like an eclipse conformation, so it has very high, or we'll say maximal torsion and angle. Strain. We're talking about different kinds of strain. What was the other kind of strain I went over? Think about it. Steric strain. We're not talking about steric strain right now. Okay? So you go to a 5. Now, when you go to a 5, you feel like it's a lot more flexible, and then the energy of it is very close to a straight chain compound. And this is one of the reasons 5-membered rings and 6-membered rings are ubiquitous in nature, in natural compounds, and in biomolecules, because they are stable. all right? They're very much like straight chain compounds. This is one of the reasons we said this is not a functional group. Now, a cyclopropane has tremendous reactivity, but these are also found in nature, very, very rarely, sometimes in lipids. But these are ubiquitous. They're all over the place. Why? Because they almost have the same stability as a straight chain compound. We can make them very easily in the lab. So, and you look at it and you say, yeah, this is pretty flexible. Now, how do they normally exist? They normally exist in what is called an envelope conformation. Okay? Now, what is an envelope? You would look at your 5-membered ring as though it was an envelope you were about to mail. This is the pocket down here, and this is the flap. And what you would do is you take your envelope and partially close the flap like that. What does that do for the molecule? It has a tremendous effect. If you study this, you will see that if you look down the flap bonds, there's tremendous relief of torsion. And Clem, I don't know if you can see, there's a big these are really far apart. And if you look down the other flap, it's the same deal. Okay, so there's the other flap. There's relief of strain on the pocket. So we should have made, maybe we should have made this all different colors, I don't know. But if you look on the pocket bond, which is right here where my hand is, there's some relief of torsion, and there's relief on the other side of the pocket. But you know where you have terrible torsion? On the bottom of your envelope. You see they're completely eclipsed. So an envelope conformation is really great, except for this one bond. It's not static, though. It's not like it sits in one envelope all the time. It's always moving, right? Molecules are dynamic, all right? That's what we're going to get more into this week. But this kind of gives you an idea, like if you were going to take an average picture, that's kind of what the molecule's like, all right? I'm going to spend a little more time on that in class. I really hope you watch this because it'll really help us in class. All right, the most like a straight chain compound is a cyclohexane, and we really devote 99.9% of our study to cyclohexane, okay? Again, ubiquitous in nature, very easy to make, just like a straight chain compound. Again, we didn't say it was a functional group. It's just it's a frame that you build on in organic molecules to make useful molecules. Now, how does cyclohexane sit most of the, and when you get it, you'll go, wow, it's really flexible. It'll be great. Like you can move it all over the place. If you have your little weird models from class, your little guys, these are not as flexible, but you'll find it's quite flexible. All right. How does it sit most of the time? It sits in what's called a chair. Now, these terms are very descriptive, and they're very helpful, I think. But it spends most of its time in a chair. I don't know if you can get the whole thing in. All right. What is the chair? It's like a lawn chair. It's like the kind of lawn chair we used to have in the old days. Maybe they still have these. The lawn chair they still have these. The lawn chair has a back, right? A place where you sit, and then a footrest. You know those kind of lawn chairs? The hinges for the lawn chair are like right here and right here, right where I have my blue and where I have my green. Okay? And what the molecule is thought to do is to flip between this lawn chair, okay, which I have, and the other lawn chair. And that would involve the backrest going down to be a footrest, and then the footrest coming up to be a backrest. Now, do you see I have the opposite lawn chair? So there's the back. There's where you'd sit. That's where your feet would go. So again, I'm going to flip again. This is another way I could flip. I could take the footrest up. This would be like you're laying in your lawn chair with your feet up in the sun, right, like this. Backrest down. That gives you the other chair. Now, there are actually a multitude of conformers that exist in between. Okay? It's really thought that the molecule goes from a chair to a half chair. And I want you to look at the half chair in terms of torsion, because the half chair has a lot of torsion on the bottom. It's a high energy conformer. Then it goes into what's called a twist boat, into the boat. This is called a boat. To another twist boat. I'm going to have to do this in class. Half chair on the other side, and then to the other chair. But what do you guys do? You're going to do this. This is your life. Your life is really going to be like, I'm going to go to the boat, then I go to the other chair. But there's a lot of stuff happening in between, and I'll go over that in class. Okay? What I want to do now is just get you kind of your feet wet drawing these chairs, because I could spend a lot of time talking about the energy of the flip, and I'm going to do that in class. I'm going to spend my class time on that, but I'm going to give you an art lesson on how to draw these. And Clem, how much time have I used?
9:40.
Okay. Now with your models, by the way, the models you guys have, if you want to make a chair, this is what I would suggest. Pull, what do I suggest? These are very wobbly. Pull it up, make the boat, because I think if you make a good boat, oh gosh, if you make a good boat, you'll be happy. So like put everything in one plane, like the way we were doing it earlier. Take opposing hydrogens and pull them toward each other, like I showed you with the cyclobutane. And then when you do that, if you have 4 bonds going more or less straight down, and these two punching into each other. By the way, this is a steric interaction, and it's called a flagpole interaction. We'll talk about that in class. Take one of those flagpoles and just pull it down, okay? And then you'll have a boat. Then you'll have a chair with your models, okay? So make a boat because they're easy to make, and then take the footrest of the boat and bring it down so it's really a footrest. My models, these models, if anyone has these in smaller versions, these are great for this particular application. All right, in terms of drawing it, I'm going to start you with a very simple way to draw it. Okay, so I want you to realize that when you're drawing a chair flip, and you'll start to see why this is so important, but when you're doing a chair flip, there's a lot going on in the molecule. And that's what we're going to get into in class, all right? This is just kind of like your primer into that. All right, there's a lot changes in the molecule in that seemingly innocent flip that occurs, especially if there's a substituent on the ring, and that's what we want to get into. Now, this is my lawn chair. I just drew it for you. This is a side view of the molecule. So in other words, I'm looking at the molecule from the side like that. This part of it over here is in the back, and this part is in the front. Anything that's lower is in the front. So this is really, you don't have to do this. Please don't start doing this. It becomes terrible when people do this. You don't have to draw this. People make an assumption about these, but this is really in the back, but you don't have to do that. This is sitting right in the plane of the board. This is sitting right in the plane of the board. This is where the hinges are, there and there. Now, when I start people, I draw them like lawn chairs. In other words, you could be sitting here, like your body would be here, very long body, feet there, arms here. That's you sitting in the lawn chair, okay? So when you flip the chair, essentially what you do is you take this piece when you're drawing it. And again, this is a side view. We're not looking at it like this. We're looking at it like this. We're taking the back of that and bringing it down. And then we're bringing the footrest up like that. Don't always put a person in it. It gets very messy. But his feet are going to go flying up, right? So when you flip the chair, it's like you're bringing this up to make the boat, and then you're bringing this down to make the new chair. What would that look like? Well, you guys are stereochemists. You know it'll look like a mirror image. Okay, these are the hinges. Okay, that's a chair flip. But believe it or not, what we're really interested in are where the hydrogens are on this. And that's what I want you to practice, okay? This is really about getting your feet wet, so when we go through this, it doesn't take us hours and hours and hours. Okay, so I'm going to draw a new chair here. Now, I'm going to draw them a little more pitched next week. Okay, that's a terrible looking chair. Let me get rid of that. This one was pretty good. There's another way to draw them that is perfectly respectable, but this is usually how I start people. The basic deal is, if the carbon is pointing down, even if it's slightly down, you draw one hydrogen straight down, and you draw one hydrogen slightly up. We call this axial down, and we call this equatorial up, okay? And basically, I'm almost done. Basically, if it's going down, you go, oh, I just did down. If a carbon is pointing up, you draw the hydrogen straight up, which is axial up. And you know, in organic, there's always a lot of terminology. Equatorial down. That's why it's good training for everything, okay? All right, so let me get rid of this guy. All right, so say I've got 2 chairs. What I want you to do before class, now I pitched that a little bit. They're going to be a little more pitched like that, the lawn chairs. I want you to learn how to fill your hydrogens in. I remember when I was in college spending like an hour just practicing drawing these hydrogens, so it was second nature to me. Okay? So this carbon is pointing up. It looks like a little arrow pointing up. That means I have to put one hydrogen straight up, one slightly down. This is called axial up. I'll put A up, AU, and equatorial down. That's down. Okay, wait till you see what cis and trans is on these things. Now this, though it's not wildly down, this is a little arrow pointing down. So this is equatorial up. What am I trying to do here? There's nothing too exciting about what I'm doing. What I'm doing is I am drawing tetrahedrons. That's all I'm doing in this little puckered shape that the chair really assumes. I mean, it's kind of ridiculous to assume that this thing sits flat like this. It's very strained for it to sit flat like this. But when it sits like this, it doesn't have any, you're going to see it doesn't have any torsional strain on any bond. That's what's so great about six-membered rings. Play with it. All right, so if I keep going, right, this is a little arrow pointing up, so I'm going to put one hydrogen straight up, axial up, one slightly down like that, equatorial down. Down, up, up, down, up, slightly down, axial. Do it for this one as well. And get it to work with your model. You know, take a look at your model. Some of you don't want to crack the models out. I would. I'm not totally against models. I'm also not totally against the supplemental textbooks you use. All right? You can ask me questions about them. It's okay. But these, right, if you look at my chair that I have here, it has 3 bonds that are going straight up. Those are the axials. And notice it has these lovely hydrogens undulating around the midsection here. Those are the equatorial hydrogens. And then on the bottom, it has 3 axials. So we need to learn how to draw that on a piece of paper. Do it on this one for Monday. Try to fill them in. It'll really help you move along when we get back. Because we have to get into reactions next week. It's very important. Next week is also NMR week. And we're really going to be working hard on NMR. So get ready. Okay? Okay. We're done. Thanks.